Chopper drives. Chopper drives are widely used in traction applications all over the world. A DC chopper is connected between a fixed voltage DC source and a DC motor to vary the armature voltage. In addition to the armature voltage control, a DC chopper can provide regenerative braking of the motor and can return energy back to the supply. This energy saving feature is particularly attractive to transportation system with frequent stops such as mass rapid transit, that is MRT. Chopper drives are also used in battery electric vehicles, that is BEVs. A DC motor can be operated in one of the four quadrants by controlling the armature and or the field voltage or the currents. It is often required to reverse the armature or field terminals in order to operate the motor in the desired quadrant. If the supply is non-receptive during the regenerative braking, the line voltage would increase and the regenerative braking may not be possible. In this case, an alternative form of braking is necessary, such as rheostatic braking. The possible control modes of the DC chopper drive are: first one, power or acceleration control; the second one, regenerative brake control; third one, rheostatic brake control; and the fourth one, combined regenerative and rheostatic brake control. First one, the principle of power control or the acceleration control. The chopper is used to control the armature voltage of a DC motor. The circuit arrangement of chopper-fed DC separately excited motor is shown here. The chopper switch can be a transistor or forced commutator thyristor chopper. This is an one-quadrant drive. The waveforms for the armature voltage, load current, and input current are as shown, assuming highly inductive load. Then, the current Is will be present at IA when the chopper is turned on. So KT is the area where the chopper is turned on, or T on period. This is total period. Then the voltage Vs is going to appear across the VA when the chopper is turned on. When the chopper or transistor is off, the voltage is going to appear across the chopper. The current through the armature IA will be constant. When the chopper is there, the current will be there, but when chopper is turned off, due to the freewheeling diode, due to the highly inductive load here, the current will flow through the motor, so the current will be available even in turn-off period of the chopper. Then available. The average armature voltage VA is given by the K Vs, where K is the duty cycle of the chopper. The power supply to the motor is given by P naught equals to VA IA, which equals to K Vs IA. Let it be 1, 2. Where IA is the average armature current of the motor and it is ripple free. Assuming a lossless chopper, the input power Pi is given by P naught, that equals to K Vs Is. The average value of the input current Is is given by K IA. Question number 3. The equivalent input resistance of the chopper seen from the source is equals to, or equivalent equals to, Vs divided by Is, that equals to Vs divided by Ia 1 by K. Let this be question number 4. By varying the duty cycle K, the power flow of the motor can be controlled. By controlling the power flow to the motor, we can control the speed of the motor. For a finite armature circuit, inductance can be applied to find the maximum peak-to-peak ripple current as delta I max equals to Vs by Rm tan H of Rm divided by 4f Lm. Question number 5. Where Rm, Lm are the total armature circuit resistance and the inductance respectively. For separately excited DC motor, the Rm equals to Ra plus any resistance in series, and Lm equals to La plus any inductance in series. For series motor, Rm equals to Ra plus Rf plus any resistance in series, and Lm equals to La plus any inductance in series. Principle of regenerative brake control. In regenerative braking, the motor acts as a generator and the kinetic energy of the motor and the load is returned back to the supply. The principle of energy transfer from one DC source to another higher voltage is applied in regenerative braking of a DC motor. The application of DC chopper in regenerative braking can be explained with the help of this circuit. It requires rearranging the switch from powering mode to regenerative braking. Let us assume that the armature of the separately excited DC motor is rotating due to the inertia of the motor, and in case of transportation system, the kinetic energy of the vehicle or train would rotate the armature shaft. Then, if the transistor is switched on, the armature current will rise due to the short circuiting of the motor terminals. If the chopper is turned off, diode DM would be turned on and the energy stored in the armature circuit inductance would be transferred to the source to the supply, provided that the supply is receptive. It is a one quadrant drive, operates in second quadrant. The voltage and current waveforms, assuming that the armature current is continuous and ripple free. When the chopper is off, then the current will be there, IS, and IC. When the chopper is on, then the current IC will be there. The chopper voltage will be present when the chopper is turned off. Then the current through the motor IA will be continuous. Average voltage across the chopper is given by VCH equals to 1 minus K Vs. Let this be equation number 6. If IA is the average armature current, the regenerative power can be found PG equals to IA Vs 1 minus K. Let it be 7. The voltage generated by the motor acting as a generator is given by EG equals to kV IA omega, that equals to VCH plus RM IA. Then VCH is nothing but 1 minus K of Vs plus RM IA. That is equation number 8, where kV is the mission constant and omega is the mission speed, radians per second. Therefore, the equivalent load resistance of the motor acting as a generator is given by R equivalent equals to EG by IA, that equals to Vs divided by IA 1 minus K plus Rm. Let this be 9. By varying the duty cycle K, the equivalent load resistance seen by the motor can be varied from Rm to Vs by IA plus Rm, and the regenerative power can be controlled. The conditions for permissible potential and polarity of the two voltages are 0 less than or equal to EG minus Rm IA less than or equal to Vs. Let this be equation number 10, which gives the minimum braking speed of the motor as EG equals to kV omega minimum IF, which equals to Im IA Rm, or omega minimum equals to Rm by kV IA by IF. Let this be equation number 11. And omega is greater than or equals to omega minimum. The maximum braking speed of the series motor can be found from equation 10, that kV omega maximum IF minus Rm IA equals to Vs, or omega maximum equals to Vs divided by kV IF plus Rm IA divided by kV IF. Let this be equation number 12. And here omega is less than or equal to omega max. The regenerative braking would be effective only if the motor speed is in between these two limits, that is omega minimum less than or equal to omega less than or equal to omega maximum. At any speed less than omega minimum, an alternative braking arrangement would be required. Although DC series motors are traditionally used for traction applications, due to their high starting torques, a series excited generator is unstable when working into a fixed voltage supply. Thus, for running on the traction supply, a separate excitation control is required, and such an arrangement of the series motor is normally sensitive to the supply voltage fluctuations, and a fast dynamic response is required to provide an adequate brake control. The application of DC chopper allows the regenerative braking of the DC series motor due to its fast dynamic response. A separately excited DC motor is suitable in regenerative braking. The armature and field can be controlled independently to provide the required torque during the starting. A chopper-fed series and separately excited DC motors are both suitable for traction applications. Third one, the principle of rheostatic brake control. In rheostatic braking, the energy is dissipated in the rheostat and it may not be a desirable feature. The mass rapid transit MRT systems, the energy may be used in heating the trains. The rheostatic braking is also known as dynamic braking. As the arrangement for the rheostatic braking of a DC separately excited motor is shown in the circuit, this is one quadrant operation in second quadrant as shown here. Waveforms for the current and the voltage, assuming that the armature current is continuous and ripple free. When the CH is on, the current will flow through the CH. The voltage appears across the CH when CH is off, which is equals to the voltage VB, that is nothing but RB IB, and the current through the motor is continuous as it is highly inductive. The average current of the braking resistor IB equals to IA 1 minus K. Let this be question number 13. The average voltage across the braking resistor VB equals to RB IA 1 minus K. Let this be equation number 14. The equivalent load resistance R equivalent equals to VB by IA, which equals to RB 1 minus K plus RM. Let this be equation number 15. The power dissipated in the resistor RB is given by PB equals to IA square RB 1 minus K. Let this be equation number 16. By controlling the duty cycle K, the effective load resistance can be varied from Rm to Rm plus Rb, and the braking power can be controlled. The braking resistance Rb determines the maximum voltage rating of the chopper. Fourth one, the principle of combined regenerative and rheostatic brake control. Regenerative braking is energy efficient braking. On the other hand, the energy dissipated as heat in the rheostatic braking. If the supply is partly receptive, which is normally the case in practical traction system, a combined regenerative and rheostatic braking control would be most energy efficient. An arrangement in which rheostatic braking is combined with the regenerative braking is shown in this circuit. During regenerative braking, the line voltage is sensed continuously. If it exceeds a certain preset value, normally 20% above line voltage, the regenerative braking is removed and rheostatic braking is applied. It allows an almost instantaneous transfer from regenerative to rheostatic braking if the line becomes non-receptive, even momentarily. In every cycle, the logic circuit determines the receptivity of the supply. If it is non-receptive, thyristor TR is turned on to divert the motor current to the resistor RB. Thyristor TR is self-commutated when the transistor Q1 is turned on in the next cycle. This is how the principle of combined regenerative and rheostatic brake control is going to work. This is about the chopper drives and 4 different control strategies used in the chopper drives. If this video is useful, like, share, subscribe and comment. Thank you.